I'm going to make a little review video for mechanics. We have an exam tomorrow. So the first stuff we need to cover is basically Newton laws over here. So I kind of have this little chart where I drew this all out. Here's some Newton laws. We got basically the force equals zero and acceleration equals zero. Torque equals zero, then the angular acceleration is equal to zero. Here you have momentum constant or angular momentum to be constant. And here are the other two laws. This is the first one. Then you got F equals ma, which is what we all sort of have to sort of start with if we're thinking about this force in relation to other forces. This is the third law, which just says that two forces are equal and opposite. This is kind of simple stuff. But and the idea is when we take the F equals ma, you can start to ask yourself, what are all the possible types of forces that we can have? And here's sort of some of them. So you got you could write it in velocity form like this, or you could write it in mass flow form like this. You could write it in centripetal acceleration like this. You can think about linear drag, turbulent drag. These are the two forms. In fact, these are two forces that are really important for this exam, is the linear drag and the turbulent drag. Um, right, yeah, so that's basically going to be this one's linear and this one's turbulent. And when you sum them together, you get this idea, which is like negative BV minus CV squared, which is cool. The next section here we kind of need to think about is space and time. So let's consider the kinematic equations here. And so these are like five equations. So you got v squared equals v final squared equals v naught squared plus 2a delta x. Vf equals vf plus at. V naught plus at. And then probably the most important one that we always need to use is this one, or delta x is equal to v naught t plus 1 half at squared. Usually this is the one that's the most important. Although this one's really important, and also this one's pretty important because they each have specific purpose. Like, if you don't have time, you can use this one. If you don't have position, you can use this one. If you don't have, this one's good, but I think if you don't have the final velocity, you can use this one. So, you know, each one of the, and also this all assumes that acceleration is constant. So if you don't have constant acceleration, you can't use the regular kinematics. You have to go to like general relativity or something, or special relativity. Anyway, so then we have mass and force. We already sort of took a look at how momentum could be constant, but the mass and the force, here's another idea again, we already talked about that. And the momentum is really important. So like momentum is basically, like the change of momentum is the impulse, the integral over time of the force. Usually we do an integral over distance of the force. But if we do that, then we get work over here. Integral of distance over force. Here it is. Integral of distance with the force, we get work. But if you integrate the force over time, you get the impulse. And that's the change of momentum versus the change of kinetic energy. All right? So that's kind of interesting. We got basically these symmetries and these parallels between these things. Um, the change of momentum, it's kind of a messy little chart I have here, so, you know, bear with me here. The momentum is just mass times volume, and we like to think about this rocket stuff and how the momentum changes for the rockets, but think about that probably a little bit later. We already discussed the conservation laws, and sometimes we have to break apart the forces into three components. You can see we could break it up into the x, y, and z components. And then this part here about the two-dimensional polar coordinates, I wanted to go through the derivation of this acceleration because that's pretty important. So if we're going from regular Cartesian coordinates, which would be like x and y hat right here, and we want to switch that over to polar coordinates, and we want to figure out what this acceleration is, the way to do that is we take our r hat and our theta hat, and this comes from like rotation matrices and stuff. So then we have the cosine plus sine, negative sine plus cosine, and if you take derivatives of that, you'll notice that if you take the derivative of this, you'll get negative sine cosine, and then times the chain rule here with the derivative of theta. So you get this. Similarly with this, you kind of get negative r hat. So that's kind of interesting. And then we'll look at the position vector, take a derivative of that using the chain rule, or we're using the product rule here, I guess. And then that's velocity. I'm going to make the replacement over here with r hat, um, dotted r hat. That's like r hat prime or whatever. And then here, this is just, again, you take in the derivative, so you have to do another massive product rule. So you get a double product rule here, and you get a triple product rule here. You just take in a derivative of this, a derivative of that, and a derivative of this. And you try to do the replacements of this r hat prime and the theta hat prime, and all of a sudden you can get the acceleration. It's kind of an interesting derivation here, but that's what we got to do. So that's how we can start to change coordinate systems. Well, let's go back into this air resistance stuff because it's pretty important. It's probably what this exam is going to be mostly about. So again, we have the two equations. It's kind of up here. This one, and when you take the like ratio between the linear and the quadratic form, you get Reynolds number divided by 48. If Reynolds number equals 1, then you have to consider both drags. If the Reynolds number is really small, then you focus on the linear drag. If the Reynolds number is really big, then you focus on the quadratic drag. Um, this is the better equation to use rather than all of this. But here you can notice that we could replace B with a beta d, and d is the radius times 2. It's the diameter of like a ball. So usually we're thinking about a drag of an object with like a little ball with a radius or diameter, and so that's what we're considering is like a section. And so you get beta. Here's the number for beta, and then over here we have c. So you can do cv squared, but c is equal to gamma times d squared. So that's the number for gamma. And then we have this tau constant. Well, tau is just m divided by c v naught in this particular situation here. I think it's better to just look at the terminal velocities, because you have terminal velocity is mg divided by b when you're just focusing on linear drag. Then you have terminal velocity be square root of mg divided by c if you're doing the quadratic. And that makes sense. You know, you have v squared, it gives you a square root. If you have just regular v, you just get the regular v. Alright, so that's good for the drag forces. There are a whole bunch of other forces, but they're not really relevant. Maybe friction might be relevant in this. Maybe this change of the work or the change of the energy in terms of position. You take the derivative of that, you get force back out of that. And the gravitational force, it's probably going to be more like U equals mgh is most likely what we're gonna be focusing on. Probably not going to use this type of g and m over d squared form. And we also might look at Lorentz force, which is well, no, just regular old force of magnetism. So magnetic force Q V cross B. Don't know if I even have that here because it's kind of an advanced force. If you want to take the cross product, there are some easy ways to do that. You could set it up like this, where you write the vector twice ABC, ABC, and then the other vector XYZ, XYZ. You cut off these two sections, and then you can cross the middles, and you can get your answer just like that. That's one way to do it, although there's another way to do the cross products, although it's not so important. As long as you can do it real quickly, it's nice. Complex exponentials, yeah, we should be able to use Euler's formula and stuff, but I don't think that's all that necessary. Let's look at the conservation of momentum here. Conservation of momentum basically always says that the initial momentum is equal to the final momentum, and the change in momentum equals 0. Also, that xcom initial equals xcom final. That's a good one. And here's the center of mass. In fact, that's probably like down here we have the center of mass. So like the cool thing is that the center of mass doesn't move. There's like a cool rule that I think the center of mass moves, but the object doesn't or something. Or no, maybe they're like objects together that the objects can move, but the center of mass doesn't. Anyway, there's like a cool rule out of that, which I might have to write down later. I don't think I wrote it here. Um, Here's a way to get dm in terms of the densities. Because remember, we have to do this integral r dm divided by integral dm. You could also follow vcom. And here are inelastic collisions where you have the initial momentum is equal to final momentum, but the kinetic energies are different. Or the elastic collisions where you also have the kinetic energy equal to the final energy. And for these rockets, we have these Tchaikovsky Vf minus Vi equals V exit ln mi over mf. And you can set up the differential equations if you want to try to solve it. Here's the rocket's draining field mass. Angular momentum for a single particle. Yeah, so the angular momentum, and over here, it's a cross product. I think of it as pork instead of torque, because we're doing R cross P instead of R cross F. But anyway, so R cross F equals the torque. That's interesting. So here's torque, it's equal to I alpha. Here's how you could set this up. Nice and quick shortcut. RF equals I alpha. And here is the idea that the derivative of the angular momentum is equal to the exterior torque because the internal forces tend to cancel. We already kind of looked at the kinetic energy and work though. Just real quick, back to the kinetic energy idea and the work. Negative work is equal to the change of potential energy. And here's MGH formula. And then you can do the integral of force over distance. There's a lot of ways to get this work integral. You do it at pressure and volume. Well, it's not relevant. You have delta K E also gives you work. So that's great. And the final thing is basically that we could take the gradient of the potential energy, but these two things, these potential energy, these conservative forces, change of the energy is 0 if conservative. Okay, so that's interesting. I think that conservative forces were, aha, so F dot dr, but then also the other idea is that the cross product of the force is equal to 0. Boom. Both these two things are true if we have a conservative force. That's why it's important to know how to do the dot product with the integral. It's actually very easy. That's Kind of what it is. We're doing basically like taking a del and then the nabla and multiplying it by the function. So you just go boom, boom. This is supposed to be, if you're doing a dot product, then this would be ux, like the x component of u. Here, you're not doing a dot product, so you're doing full u derivative. Hopefully this kind of makes a little bit of sense. Anyway, this is what we're covering in the first couple of chapters here for our exam for mechanics. And if you wanted to download this cheat sheet, I will leave a link at the bottom. There's actually three versions. This is like the advanced version. But take a look at the initial version. Very simple. It's only got a couple of equations. It's much more organized. This one here is pretty nice. It's good to have right there. The second version has a little bit more info on it because, well, mechanics is a big topic. You can see it starts to get pretty expansive, but still reasonable, quite reasonable. It's the final sheet right here that I'm working on right now because, well, mechanics just gets crazy. So much stuff. So anyway, hopefully this is some good stuff. If you want to download this, I'll leave a link at the bottom of this video. Y'all have an awesome day and thank you so much for